Let me give you the 30,000 foot view of what stoichiometry is. Stoichiometry. And I'm going to tell you now that stoichiometry is actually super easy. And the reason why I call it the 30,000 foot view is because if you look at it and you're so fixated on it, then it's going to look complicated and very confusing and very frustrating and hard. But if you zoom out, if you go onto an airplane and you look down, you can start to see the big picture. And when you see the big picture, you realize how easy stoichiometry in itself is. Now, I'm not going to say that this section is actually really easy. This section is really hard. And if you ask any student who learns stoichiometry for the first time, or even any student who learns stoichiometry for the second time, they're going to tell you that this is really, really hard stuff. Let me kind of show you what we're getting at here and the approach that we're taking, because I'm actually going to try to convince you that this is not that bad. So let's see. Let's do a checklist of what you know how to do so far. You are masters at writing a balanced equation. Which is actually not that easy in itself, because with a balanced equation you need to know nomenclature. That's essentially, you need to be able to take a chemical formula and write it into, or a chemical name and write it into a formula. And for that you need oxidation numbers and all of that kind of stuff. And then not only that, but you need to balance the thing, and that can be really tough. It's not necessarily, yeah, well, that's balancing the equation. You know how to do that already. All right, you also are pretty good at converting mass into moles, and vice versa, right? You're pretty good at that. And to do that, we use the molar mass that we found inside of the periodic table. I'm going to put molar mass. Okay. And then you've gotten good also at converting the number or atoms or particles into moles. And use 6.022 times 10 to the 23 things equals 1 mole. So none of this is stoichiometry. These is separate things that we've covered before, and I'm not saying that any of these things are actually really easy, but they're not really that bad, and we're pretty well versed in this. You're also really good at converting converting, like using the big parentheses to convert from one unit to another unit. You're very good at that. So what stoichiometry is it's kind of using all of these things. We're going to, in essence, in the end, we're going to show you how to use all of these tricks put together. Now, the way I look at stoichiometry is all it is it's going from 1 moles, so the moles of something, to the moles of something else via some kind of bridge. And that bridge uses the balanced equation. Let me show you what I mean by this, and we'll go with this example, 9-11, and you're going to see how easy this is, and then you're going to see, wait a second, I can see how he's going to add a whole bunch of stuff to it to make it really painful. So if I say, all right, if 25.0 moles of diphosphorus pentoxide reacts with water to form phosphoric acid, how many moles of water is required? Okay. And then they also give us the balanced equation, which takes care of this skill that we needed to know how to do, because I could have easily not given you the balanced equation, and then it would become a very painful problem. But anyway, P2O5, not impossible, just a little bit more painful because you're dealing with a few more steps. But anyway, they already gave us the balanced equation, so we don't even need to use the coefficients to balance this thing. H3PO4. Cool. Now, just because I like doing this, I'm going to make sure that I'm dealing with a balanced equation. Let's see. There are 2 P's on both sides. There are, I see 5 O's plus another 3, so that's 8 O's on one side and 8 O's on the other. And I see 6 H's altogether. All right, cool. So they did indeed give us a balanced equation. Now, see these coefficients right here? If there's nothing there, it's an implied 1. And these coefficients right here, that is saying 1 mole of diphosphorus pentoxide combined with 3 moles of water gives me 2 moles of phosphoric acid. So, in essence, if I say, well, I'm starting off with, I guess what I'm saying is this gives me a whole bunch of equal signs. This is saying 1 mole of P2O5 doesn't equal to, but I mean it's related to 3 moles of water. Or I can even do this equal sign. 1 mole of P2O5 is related to 2 moles of H3PO4. I can really make any of these equality statements based off of just the numbers that I'm getting out in front here. And so that's actually pretty simple because, I mean, I can go from water to phosphoric acid. I can go from 3 moles of water, H2O, gives me 2 moles of H3PO4. And the problem says I start off with 25 moles of this stuff. So 25 moles, or actually 25.0 moles of P2O5. And I want to convert that to moles of water. I want to see how many moles of water is reacted in there. So let's see. I would like to use the equality statement that deals with the P2O5 and the water. So there it goes. Now from this equality statement, I'm going to make a fraction. And I can choose to have the fraction where I have moles of H2O on the bottom or moles of H2O on the top. Or maybe I can say in the other way, moles of P2O5 on the bottom or moles of P2O5 on the top. Which fraction should I choose? Well, I'm going to choose the one where I have 1 mole of P2O5 on the bottom, and that's associated with the 3 moles of H2O that is required to react with that P2O5. And I like, the reason why I put that on the bottom is because it's in the numerator over here, so I'm going to cancel that out. None of this is pretty difficult. And then I have 25 times 3, and that gives me 75. 75 moles. Actually, I probably should put 75.0 just to make it correct sig figs of water is required to react with 1 mole of this P2O5. On the surface, to be honest with you, that was not hard at all. And I'm sure that you guys are thinking, wow, that's not hard. And my answer is, you're right, it isn't. It isn't hard at all. But here's the things that we can add to this to make your life harder. And we will, and we absolutely will. And this is what everyone says makes stoichiometry hard. Because in essence, I see crossing this bridge as the stoichiometry step. And that was not hard. That was exactly what we did here. The thing that will make it hard is I could give you the question without giving you a balanced equation. Well, to do that, you would have to go through the nomenclature and then go through balancing the equation with the coefficients, and then, you know, it's just these extra steps. But it doesn't make the stoichiometry crossing that bridge hard. It just makes setting up that bridge hard. And here's the other key. In order to cross that bridge, this only works when going from moles to moles. Because these coefficients out in front represent moles. They don't represent grams, they don't represent atoms, they don't represent liters or whatever, they represent moles. So I could be a real punk and give you the question and say, well, I'm starting off with this mass of something. How many moles will I have in the end? Well, first you need to be able to get from mass to moles. And then you can cross the bridge using stoichiometry, and then you're done because your final destination is moles in the end. Now, going from mass to moles, that requires you to understand molar mass. Not particularly hard, just, another step. Or I could be a punk and say, well, I was starting off with the mass of something, and I want to get the mass of something else in the end. So that also requires a molar mass. Keep in mind that this molar mass is going to be different from this molar mass. This molar mass would be the molar mass of the substance going in. So in this case, it would be the P2O5. And this molar mass would be the molar mass of the water. So if I started the problem and I told you, hey, I'm doing a stoichiometry problem, I'm not going to give you the balance equation, and I'm going from mass to mass, then you're going to be like, well, the stoichiometry part isn't really that bad, but this punk right here is making me convert from mass to moles using the molar mass, and then I got to write the equation down and balance it out so I can cross this bridge using stoichiometry, the easy step, and then I got to use the molar mass to convert it back. And I say, yes, it's exactly what you need to do. Now, that doesn't necessarily say that the stoichiometry part was difficult, but it does make it so that, the other parts, the bridge wasn't hard. It's creating the bridge was hard. It's converting this was, actually creating the bridge wasn't hard actually. But creating the bridge took a step. Converting this thing took a step. Converting it backwards took another step. And so when you combine those three easy steps, all of a sudden it becomes a hard problem. And I would say, no, it just becomes a longer problem. All right, here's another punk move I could do. I could say, well, I'm not going to give you the mass. I'm going to tell you the number of particles or atoms. And now you got to now you got to tell me, I'm going to start off with this number of atoms. I want to figure out what the mass is. And my answer would be, well, in order to get from atoms to moles, because we need to get to moles in order to start the first leg of this bridge, I need to use Avogadro's number, and that would be the 6.022 times 10 to the 23rd things equals 1 mole. And say that, so then I start with Avogadro's number, go down to moles, cross the bridge with the balance equation, then convert using the molar mass to the mass. All not necessarily hard steps, just a bunch of mediocre steps put together, making it seem like it's really complicated and really hard. Or say that I want to go and do this, and I want to convert, I want it to have atoms in the end. Well, then you're going to have to go Avogadro's number in the end. And there's going to be one more thing that I'm going to add to this that I'm not going to teach you now because it's actually covered in the next chapter, which deals with volumes and gas and ideal gas and all of that kind of stuff. But essentially, this is what makes stoichiometry the hardest thing that all students hate, but really it's not. It's gotten a bad rap because stoichiometry is really actually this easy. It's all of these other wings that make it hard.